According to NEC 480.10c, specifically regarding the equipment grounding conductor, the equipment grounding conductor is permitted to be connected to the grounding electrode system at any convenient location. Let's break down the different methods for connecting the equipment grounding conductor to the grounding electrode system. Firstly, electrode conductor. The equipment grounding conductor is permitted to be connected to the grounding electrode system by means of the grounding electrode conductor. This means that the equipment grounding conductor can be connected to the grounding electrode conductor, which then connects to the grounding electrode. Secondly, grounding electrode. The equipment grounding conductor is permitted to be connected to the grounding electrode system by means of a grounding electrode. This allows for a direct connection from the equipment grounding conductor to the grounding electrode itself. Thirdly, water pipe. The equipment grounding conductor is permitted to be connected to the grounding electrode system by means of a metal water pipe at any convenient location along the length of the pipe. This option allows you to use a metal water pipe as part of your grounding electrode system and connect the equipment grounding conductor to it. Fourthly, building steel. The equipment grounding conductor is permitted to be connected to the grounding electrode system by means of building steel in accordance with 250.50. If the building has a metal frame, it can be used as part of the grounding electrode system, and the equipment grounding conductor can be connected to it, following the requirements in section 250.50 of the NEC. Fifthly, concrete encased electrode. The equipment grounding conductor is permitted to be connected to the grounding electrode system by means of a concrete encased electrode in accordance with 250.52. This method uses a concrete encased electrode, often referred to as a UFA ground, as part of the grounding electrode system as described in 250.52 of the NEC. Sixthly, grounded conductor. The equipment grounding conductor is permitted to be connected to the grounding electrode system by connection to the grounded conductor of the circuit supplying the equipment. This allows for connecting the equipment grounding conductor to the grounded conductor, which is typically the neutral conductor of the circuit. So, in summary, the answer to your question is yes. The grounding electrode conductor taps from multiple service panels can indeed go directly to the water pipe electrode or building steel, and you can jumper from there to raws and concrete encased electrodes, provided that all connections and installations comply with the NEC requirements, specifically those outlined in Article 250 regarding grounding and bonding. It's important to ensure that all connections are properly made and that the grounding electrode system is effective in providing a low impedance path for fault current. Let's delve into some specific considerations for each type of grounding electrode. For the metal water pipe electrode, the NEC requires that the water pipe be in direct contact with the earth for at least 10 feet or 3.0 meters. Additionally, the water pipe must be supplemented by an additional electrode, such as a ground rod or concrete encased electrode. The connection to the water pipe should be made within 5 feet or 1.5 meters of the point where the water pipe enters the building. It's crucial to ensure that the water pipe is electrically continuous and that there are no insulating sections or unions that would interrupt the grounding path. When using building steel as a grounding electrode, the steel structure must be effectively grounded. This typically involves connecting the grounding electrode conductor to a substantial section of the building steel, such as a column or beam. The building steel must be interconnected to form a continuous grounding path throughout the structure. As with the water pipe electrode, building steel must be supplemented by an additional electrode. For concrete encased electrodes, also known as UFA grounds, the electrode must consist of at least 20 feet or 6.0 meters of bare copper conductor that is at least 4 American wire gauge in size. The conductor must be encased in concrete that is in direct contact with the earth. The concrete must be at least 2 inches or 50 millimeters thick. Concrete encased electrodes are often installed during the construction of a building, but they can also be added to existing structures. Ground rods are another common type of grounding electrode. Ground rods must be at least 8 feet or 2.4 meters long and must be driven into the earth until at least 8 feet or 2.4 meters of the rod is in contact with the soil. The NEC requires that ground rods be at least 8 feet or 2.4 meters apart. It's important to select the appropriate type and size of grounding electrode conductor for the application. The size of the grounding electrode conductor is based on the size of the service entrance conductors. NEC Table 250.66 provides guidance on selecting the appropriate size of grounding electrode conductor. When connecting grounding electrode conductors to grounding electrodes, it's important to use approved connectors and methods. The connectors must be listed for grounding and bonding purposes and must be suitable for the type of materials being connected. The connections must be made in a manner that ensures a reliable and low impedance connection. It's also important to protect the grounding electrode conductors from physical damage. The conductors should be routed in a manner that minimizes the risk of damage from impact, abrasion, or corrosion. If the conductors are exposed to physical damage, they should be protected by conduit or other suitable means. Grounding and bonding are essential for electrical safety. A properly installed grounding and bonding system helps to protect people and equipment from electrical shock and fire hazards. It also helps to ensure the proper operation of electrical equipment. When designing and installing a grounding and bonding system, it's important to follow the requirements of the NEC and other applicable standards. It's also important to consult with a qualified electrical professional to ensure that the system is properly designed and installed. Here are some additional considerations for grounding and bonding. Firstly, grounding electrode system. The grounding electrode system is the primary means of providing a low impedance path for fault current to return to the source. The grounding electrode system consists of one or more grounding electrodes that are connected together to form a single system. Secondly, bonding. Bonding is the process of connecting metal parts together to form a continuous electrical path. Bonding helps to reduce the risk of electrical shock by ensuring that all metal parts are at the same electrical potential. Thirdly, equipment. Grounding equipment. Grounding is the process of connecting the non-current carrying metal parts of electrical equipment to the grounding electrode system. Equipment grounding helps to protect people from electrical shock by providing a low impedance path for fault current to return to the source. Fourthly, ground fault circuit interrupters. Ground fault circuit interrupters are devices that are designed to protect people from electrical shock by detecting small amounts of leakage current. When a ground fault is detected, the GFCI will quickly trip the circuit, interrupting the flow of electricity and preventing electrical shock. Fifthly, surge protection. Surge protection devices are designed to protect electrical equipment from voltage surges. Voltage surges can damage or destroy sensitive electronic equipment. Surge protection devices divert the surge current to ground, protecting the equipment from damage. Remember to always consult the latest edition of the National Electrical Code for the most up-to-date requirements and guidelines on grounding and bonding. Electrical codes and standards are subject to change, so it's important to stay informed about the latest revisions. Also, it is very important to consult with a qualified electrical professional for guidance on specific applications and installations. A licensed electrician can assess the specific needs of the installation and ensure that the grounding and bonding system is properly designed and installed to meet all applicable requirements. Neglecting proper grounding and bonding can have serious consequences, including electrical shock, fire hazards, and equipment damage. It's essential to prioritize electrical safety and to ensure that all electrical work is performed by qualified professionals who are familiar with the NEC and other relevant standards. To expand on the topic of grounding electrode conductors, it's worthwhile to discuss the materials that are commonly used for these conductors. Copper is a widely used material for grounding electrode conductors due to its excellent conductivity and corrosion resistance. Copper conductors are typically available in both bare and insulated forms. Bare copper conductors are often used for direct burial applications, while insulated conductors are used for above-ground installations. Another common material for grounding electrode conductors is aluminum. Aluminum conductors are lighter and less expensive than copper conductors, but they have a lower conductivity. When using aluminum conductors, it's important to use connectors that are specifically designed for use with aluminum to prevent corrosion. In some cases, steel conductors may be used for grounding electrode conductors. Steel conductors are typically used for grounding building steel or other large metal structures. When using steel conductors, it's important to protect them from corrosion by coating them with a corrosion-resistant material. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. It's important to select the correct size of grounding electrode conductor to ensure that it can safely carry the fault current. When installing grounding electrode conductors, it's important to follow the manufacturer's instructions and the requirements of the NEC. The conductors should be installed in a manner that protects them from physical damage and corrosion. The conductors should also be properly supported and secured to prevent them from becoming loose or damaged. The connections to the grounding electrode should be made using approved connectors and methods. The connectors should be listed for grounding and bonding purposes and should be suitable for the type of materials being connected. The connections should be made in a manner that ensures a reliable and low impedance connection. In addition to the grounding electrode conductor, there are other important components of a grounding and bonding system, such as bonding jumpers and equipment grounding conductors. Bonding jumpers are used to connect metal parts together to form a continuous electrical path. Equipment grounding conductors are used to connect the non-current carrying metal parts of electrical equipment to the grounding electrode system. It's important to properly size and install these components to ensure that the grounding and bonding system is effective. Grounding and bonding are complex topics, and it's important to have a thorough understanding of the requirements of the NEC and other applicable standards. If you have any questions or concerns about grounding and bonding, it's always best to consult with a qualified electrical professional. They can help you to design and install a grounding and bonding system that meets all applicable requirements and ensures the safety of people and equipment. Let's elaborate further on the topic of connecting to different types of grounding electrodes, focusing on specific best practices and potential challenges. When connecting to a metal water pipe, it's crucial to ensure that the connection is made to a metallic portion of the pipe that is in direct contact with the earth for at least 10 feet. Avoid connecting to sections of the pipe that are insulated or have non-metallic couplings. Also, be aware of the potential for corrosion at the connection point, especially if dissimilar metals are involved. Use appropriate corrosion-resistant connectors and consider applying a protective coating to prevent corrosion. For building steel, the connection should be made to a substantial structural member, such as a column or beam. Ensure that the connection is mechanically sound and electrically conductive. If the building steel is coated or painted, remove the coating at the connection point to ensure a good electrical connection. Also, be aware of the potential for galvanic corrosion if the building steel is in contact with other metals. When connecting to a concrete encased electrode, the connection should be made to the exposed end of the reinforcing bar or conductor. Ensure that the connection is clean and free of corrosion. Use a connector that is specifically designed for use with concrete encased electrodes. Also, be aware of the potential for the concrete to crack or deteriorate over time, which could compromise the integrity of the connection. For ground rods, the connection should be made to the top of the rod using a clamp or connector that is specifically designed for this purpose. Ensure that the connection is tight and secure. Also, be aware of the potential for the rod to corrode over time, especially in corrosive soils. Consider using a corrosion-resistant ground rod or applying a protective coating to the rod. In addition to the above considerations, it's important to follow the manufacturer's instructions for all connectors and equipment used in the grounding and bonding system. Also, be sure to inspect the grounding and bonding system periodically to ensure that it is in good condition and that all connections are tight and secure. Finally, remember that grounding and bonding are essential for electrical safety. Always consult with a qualified electrical professional if you have any questions or concerns about grounding and bonding. The connections mentioned previously must be accessible. This is often accomplished with an acorn nut for ease of inspection and maintenance. The proper wire size for grounding electrode conductors is described in NEC Table 250.66, which references the size of the ungrounded conductors. It is important to recognize that smaller taps to the grounding electrode conductor are permitted, based on the size of the derived ungrounded conductors. For example, if you have multiple disconnects at a building and you are tapping to the grounding electrode conductor, the tap conductor size can be reduced to the size of the largest ungrounded conductor feeding each disconnect.